So, our last lecture of the year, and who better to finish with than to talk about Albert Einstein and his most famous equation. So, in order to do that, we have some groundwork to lay. For starters, conservation of mass slash energy, starting with classical conservation of mass. Classical physics and the general understanding of the world around us have us all under the agreement that mass is conserved. Now, what does that mean? Well, let's look at the plane on the right-hand side first. That means something we're all familiar with, which is the sum of the parts should be equal to the sum of the whole. So if each one of those pieces weighs 1 kilogram, then when put together into the full plane, it should equal 5 kilograms because there are 5 parts. Now, on the left-hand side, it's a little bit different. This is something you probably talked about in chemistry, but if you take two compounds, two materials, you put them together, even if there's a chemical reaction of some time, they blow up, something along those lines, after the fact, you will still have the same amount of mass, even if it's changed type of mass as you did beforehand. Okay, now, herein lies the problem. When we got to the turn of the 20th century, we've talked about this already, at the turn of the 20th century, there was this big issue in physics where their ability to measure more precisely and things of that nature made what we thought to be true not necessarily true anymore. So, this is the perfect, or one of the top examples. When they were able to finally measure the mass of protons and neutrons individually at that level, that tiny, tiny amount of mass, they saw this major issue come about. Now, I know that this says AU, it's atomic mass units, probably something you've talked about in chemistry class before, and we will talk about it again in a little bit of detail in a minute. But for the sake of argument, if you look on the left-hand side, the pieces of the helium atom, which is what's here, is 2 protons, 2 neutrons. And added together, those give you a mass of 4.03188. Now, if you actually combine them together into the helium nucleus, it's 4.001503. So, what the heck? Isn't it true in our everyday experience that if you add up 3 or 4 things and that's their mass, if you put them together in one bunch, the mass should still be the same? And it turns out, no, it's not. There's a seemingly loss of mass which has a name. It's called mass defect. It defects, it goes away, it seemingly disappears. Now, this is where Einstein comes into play, because at first everybody's saying, oh no, what the heck, physics is broken, everything we always known to be true is a lie. And he came up with this famous expression. I always just love this little cartoon about it. I know it's dorky, but it makes me think that if only physics were that simple. Okay, so what we have here is we have E equals mc squared, right? Now, this formula very simply allows us to discuss what happens to that mass. So if mass disappeared, what happened to it? Well, it didn't disappear per se, it became energy. So back to this picture, that mass defect isn't mass disappearing, it's becoming what's known as binding energy. And this formula, in this form or others, allows us to figure out what that binding energy would be. So, before we get into using the formula, we got to talk about some other things. As you saw before, they gave the mass, or we were able to find the mass defect even, in terms of atomic mass units. So this is what the atomic mass units say. One atomic mass unit, or U, or AMU, sometimes they'll refer to it as universal mass unit, is 1.6605 times 10 to the negative 27 kilograms. Now, while we will sometimes have to use these tiny, tiny little masses in atomic mass units as opposed to kilograms, I just reminded you that also there are situations where energy levels, where energies are going to be so tiny that they don't choose to discuss them in joules, and instead they will discuss them in electron volts, and there's your conversion also. All of these things will come into play when we do some of our math in a minute or two. So here we have our example again. So we got protons, we got neutrons, 2 protons and 2 neutrons make a helium nucleus, and that's the math that we should be looking at. Now, the chart below tells you what an atomic mass unit is in kilograms. So it's exactly 1 U, obviously. And it is 1.6605, and they added more digits to it here. So 1.660540. It goes out even further than that if you were so inclined to look at it. Now, here's one thing that always gets people. In chemistry class, a lot of times you're told that the mass of a neutron and proton are the same, and they're not. It turns out a neutron actually weighs a little bit more than a proton. And if you go further, you can argue, or some will argue, that that's because a proton is actually a neutron is actually a proton and electron coupled together with meson, which is what's holding them together in the first place. And before you sit there and allow your head to explode, don't panic. This could be an entire course in graduate level physics. So simple enough, all right? We're just going to simplify it rather. Just put it out there as kind of a fun fact. Now, what does this mean in terms of what we can calculate? Well, this first top piece was me calculating out the mass defect. It's simply just how much mass seemed to go away. So this was the mass of the 4 pieces combined together. This is the mass of when they actually got binded together. And this is how much energy seemingly went away from when you went from the parts to the whole. Now, because E equals mc squared works off of joules and kilograms and meters per second, so all the SI units, the very next thing I did after that was convert using the conversion, actually a simplified conversion, of 1 U is equal to 1.66 times 10 to the negative 27 instead of 6605 or whatever it was. Long story short, I converted the mass in atomic mass units into kilograms, and I get this. Once I have that, I can go down here, and I can calculate how much energy is basically, or how much energy that mass became. So I can find out the binding energy, let's say, of the helium atom. So it turns out when you do the math, and you can take your time and do the math yourself, it turns out to be 4.536 times 10 to the negative 5 joules. Now, there is another way of doing this conversion, or to finding this amount of energy in electron volts. Now, if you were to go this route, that's fine, and then you could just take the mass defect, go through the steps, and then do one more step, and say, well, that amount of energy, using the conversion of 1 electron volt equals 1.6 times 10 to the negative 19 joules, and you can calculate out how many electron volts of energy this is. On your reference table, they give you this conversion factor, which is super helpful. They don't actually give you that. What they tell you is something ridiculous. They say is equal to 9.31 times 10 to the second mega electron volts. But we all know that 9.31 times 10 to the second is, that's right, kids, 931. So it's kind of silly that they did it that way. So 1 U, or 1 atomic mass unit, universal mass unit, is equal to 931 mega electron volts of energy. So this has kind of run its way through E equals mc squared already. So they did some of the conversion math for you. Why is that important? Well, in a situation like this, if I asked you for that mass defect, so if I said how much energy in electron volts was the binding energy, or kind of seemingly appeared out of nowhere, you would just go directly to this math. You would say 0.030377 U, which is the difference between those two masses here, these two masses. Then you can say, well, I want to find that in mega electron volts and in electron volts. So I do a simple proportion using 1 U over 931 mega electron volts, and you get 28.65 mega electron volts. Now, remembering, or hopefully remembering, otherwise looking at your reference table, mega is 10 to the 6th. It's a prefix that represents 10 to the 6. So that is equal to 28.65 times 10 to the 6th electron volts. Or, put in proper scientific notation, 2.865 10 to 7 electron volts. Simple enough. That's really ultimately the only math. These two slides are the only math that you might ever have to do when it comes to these calculations, at least in my class. What I do want to talk about briefly is the applications. So, first application I want to talk about is this one, because I mentioned it in our lesson the other day, in a standard model lesson the other day, and then I said I'd talk about it later. So, I want to talk about it now. What we have here is we have an electron and a positron, and they're colliding together. They happen to be in the same place at the same time, which, like I said in the lecture the other day, doesn't happen often, but they are. And when they are, they collide together, and they become all energy, where ultimately they become two photons, two bits of light, which are, remember, just energy until they aren't. So they did E equals mc squared here by saying E equals 2 times the mass of an electron, because if an electron has the mass of an electron, a positron being almost identical except for the opposite charge and spin and all that stuff, it too has the same mass. So they're saying here that you would have to do 2 times the mass of an electron times c squared, and that would give you the energy that gets split into these two photons. So that's what annihilation, or they're calling it pair annihilation, is in terms of physics. Not terribly important to us. The two last applications we're going to talk about are the ones that do end up being important to us. That would be these. So nuclear fission. Nuclear fission is one of the greatest and most scary things that was ever discovered in physics. So here we have uranium-235, and we have a high-energy neutron. So that high-energy neutron is fired at E235. Now, when it's fired at E235, E235 splits. It has enough energy to make it split. Now, when it splits, that energy that was saved as kind of binding energy before now comes back out. Now, some of it becomes mass. For instance, if you look, some of it becomes 2 more neutrons, where that becomes the scary part about this, but we'll get there in a minute. But you also get 200 mega electron volts of energy in this split. So some of the mass kind of seemingly disappears again, the binding energy comes flying out, and you have a little boom. Now, why is uranium-235 in particular frightening? It's because of these two guys. Because what happens is, if this is one atom being struck by a high-energy neutron and splitting and giving you 200 mega electron volts of energy, it then gives out 2 more neutrons. Now, these 2 neutrons are free to bump into 2 more atoms of uranium, at which time they're going to split those and create energy, twice as much energy this time, and twice as many neutrons to slam into other uranium atoms, which becomes a chain reaction. Now, here's a moment that you probably never thought you'd hear. Einstein, when he first came up with this, he had great amounts of fame and fortune and all that stuff over all of this, but he didn't really see a militaristic sort of way of using this information. So it took another physicist to come to him and basically beg him to look at the math he came up with, and once he looked at the math he came up with this particular chain reaction, Einstein got really, really nervous. He and a whole bunch of the physicists around the country sent messages to the president. He actually penned his own letter to the president saying, please, 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 whatever you do, don't make this bomb. And obviously we all know what happened because, well, they didn't listen. And unfortunately, hundreds of thousands of people paid the price. Now, that's nuclear fission. Nuclear fission is also currently, in any nuclear power plant we have, the way that they create energy in a nuclear power plant. Now, they do not use uranium because it is not terribly stable and it could cause explosions, but they do use other radioactive materials, and they let them fission and fission and fission and fission, and they control how much or how little fission's happening, and they use that energy to heat up water, and then ultimately, once they've heated up the water, it turns a turbine. It turns a turbine through a magnetic field, which we talked about already. So it really just is doing the same thing as any other type of electric plant is. It's just using nuclear fuel, which seemingly is a great idea. It takes years and years and years and years and years to expend it. But the problem is once you've expended it, once you've used it for what you can use it for, it's still highly radioactive. And they need to find somewhere to put that radioactive stuff for tens of thousands of years before it's no longer dangerous to human beings. So fission, while it has a lot of great aspects to it and some horrifying ones in terms of atomic bombs, is not the best answer. Now, here we have nuclear fusion. Nuclear fusion's a little bit different because nuclear fusion is taking either helium or deuterium or tritium, usually tritium in terms of its best ability to do this, taking those things and cramming them together. Because in this particular instance, if you cram these particular atoms together, you can extract energy by the means of fusion. This is, for instance, the type of energy that is being released by the sun or any other star. You're taking hydrogen, helium, all those particles, and you're mashing them together, and you're getting a bigger particle plus some energy. Now, that neutron can then go off and could cause fission, could do any number of other things, but what will eventually happen is this particle and some other bigger particle will also fuse together, and they'll keep fusing and fusing and giving off energy and giving off energy, and this is the reason why fusion, as of now, is not the way that we power nuclear power plants, because fusion is very uncontrollable. Most of the time, luckily, it just fizzles out on its own, but it can also cause a chain reaction. So, unfortunately, when you hear about the hydrogen bomb, well, the hydrogen bomb is based on fusion. The, I guess, positive thing about the fusion bomb is that hydrogen is not radioactive. And while some of the pieces that come out of this are radioactive, the fallout, the pieces, the stuff that's left over after a hydrogen bomb is not super radioactive. It's not going to cause for much of a nuclear fallout. The major issue is fusion has, at minimum, about 10 times the yield of fission. So fusion, while it's not super radioactive and it's not dangerous as much after the fact, it is super duper duper dangerous in terms of making the bombs. Matter of fact, the proliferation, the continuation of the Cold War and the nuclear bombs that they built and made bigger and made bigger and made bigger was only possible because they discovered this technology, the ability to make hydrogen bombs. And thankfully, the Russians finally built a bomb known as the Tsar bomb. You can Google it, you can look it up. It is a frightening video to watch. And if you look at the statistics about it, it's even more frightening. I believe, don't quote me on this, it's about 1,000 times more powerful than what was dropped on Hiroshima and Nagasaki. And it created seismic waves, so basically mini earthquakes, all the way over here in the United States. So it shook, literally shook the earth. So, frightening idea. But the positive to that was when the United States saw that, even when the Russians saw that, they were far more likely to come to the table and came up with a nuclear non-proliferation treaty, which basically meant, all right, we're not making any bigger and better bombs because eventually we're going to end up blowing ourselves out of existence. Now, did they stick to it necessarily? No, they didn't make bigger bombs, they just made lots more of them, which is kind of the situation we're in now, where a lot of the countries now have them. But anyhow, not to make this into a social studies lesson, that's that. So I started with Einstein, and I want to finish with Einstein. Kind of goes along with what we were just talking about. It's become appallingly apparent that our technology has exceeded our humanity. he meant this to be about the nuclear weapons and things like that. But I think in this day and age, this could also be looked at in a lot of other ways. Now, that being said, I want to pose a problem for you guys. I want you to prove Einstein wrong. So what do I mean by that? I'm going to give you guys bonus questions or bonus points on the upcoming test if you can prove Einstein wrong. And how do I want you to do that? I want you to go on social media sometime today, and I want you to find a positive post, whether it be a quote, whether it be a quote of a great person, a great thinker, whether it be something that you put out there, even if it's just putting out there, hey, I love my family, something like that. I want you to put that out on social media. I want you to take a picture of it, snap a picture of it, and I want you to send it to me. And for every one of those that get sent to me, I will give you 5 extra points on this upcoming test. Now, for every share it gets, I'll give you an additional point on the test. Sound good? Hope it works out for us. It's been a pleasure. I'm a little sad that this is the last lecture I'm going to be giving, but it's not completely over. We have still 2 more weeks of this where we're going to do our projects. So I hope everybody is well. I hope everybody takes me up on my challenge. And I don't really care how many points I give you. Ultimately, I think this in a lot of ways is more important. All right? I'll talk to you guys soon.